Okay, good afternoon. So today I'd like to talk about special problem 2. And when we do that, it's very similar to the minimum, to the other, to special problem 1. And you'll see the difference. The difference is minor, and but also it's like a revision to the minimum principle. So let me see if I can. I want this one. All right. So in this case here, we consider a system x dot is equal to f of x and u with initial condition. The main difference we are going to consider today is when the final state is general, can be a plane, can be a surface, can be any set that belongs to or a subset of R of n, R to n, the plane of real numbers with n dimension. And if we could say that we have n-dimensional system, and we can say that the final state is anywhere in the n-dimensional system. In that case, obviously what we are saying is that the final state is free. It can be anything. It can be anything in this space. I'll give you an example and show you what I mean by that. Because function is the same, the integration from T naught to T, L, okay? And of course, U belongs to constraints. So there's constraints on U, and the experiment is defined from T naught to T1. Okay, so it's exactly the same as special problem 1, except that now we have a leeway, we have a flexibility on the final state. It doesn't have to be a specific state, and here you will see later on, I can impose a condition. Let's say I have two-dimensional system. I can impose a condition on x1 of T1, but x2 of T1 can be free, can be anything. Okay. Regularity assumptions are the same. F is continuously differentiable, and L and its derivative with respect to x are continuously differentiable, and U is piecewise continuous. So these are regular assumptions that we make all the way, in all lectures. Now, S1 is a smooth k-dimensional manifold. So this is just a general definition of a smooth k-dimensional manifold. If we define S1 as a functions that are equal to 0, right? Where Gi are smooth functions and their gradients with respect to x are linearly independent. Okay, you'll see why. So here we are just considering a smooth manifold that is it's continuously differentiable with respect to x, and the GIs here, the functions here, have gradients that are linearly independent. Okay, so Pontryagin minimum principle says is exactly the same as before, right? So if U star is optimal, then there exists a co-state P star such that, first of all, the optimal dynamics or optimal trajectories are the gradient of the Hamiltonian with respect to P, and the the co-state dynamics are the negative of the gradient of H with respect to X. And the Hamiltonian is given by this equation. Okay? This is very important. Now, this slide is the main slide that gives us how to handle this case when x of t1 belongs to S1. Okay. We need what's known as transversality or orthogonality condition. So this condition says that P star of T1, the final boundary, okay, on the costate is orthogonal to the tangent space, right, of S1 at x of T1. We call this tangent space M of x of T1, right? So we require, basically in mathematical terms, we require P star at T1, the final boundary condition on the costate, right, to be orthogonal to this plane. We call it M here, x minus x star of T1, right? So remember, this is a vector and this is a vector. If you take the transpose of that, this is a dot product, okay, times this surface, that's equal to 0. That's the definition of orthogonal if you have two vectors that are orthogonal of each other, okay? So we require P of T1 to be orthogonal to this surface here. And this tangent space, right, is defined as dgi, or the gradient of gi, or the partial derivative of gi with respect to x at x star of T1, right, times the surface is equal to 0. And I can show you, unfortunately, I don't have my pen, but I can show you how this looks like. Just give me a second. Do you people in Zoom, do you see I changed the PDF document? Do you see it now? Yes or no? Yeah, I changed the PDF. Now I'm using my cursor to point at something, at a figure. Can you see the figure? Yes? Okay, great. Okay. So I'm sharing my PDF here, so that's good. Okay. So basically, so this is the tangent M of x star. So this is the point x star at T1. This is a function or manifold of x, right? And that manifold represents the S1, which is the final surface. If you take the gradient of G at x of T1, right, that gradient should be perpendicular to the tangent. Okay, that is the condition that that we would like. So, meaning, in other words, P star should mimic or should be in the image, or should be in the what's the word? Should be in the span. Should be in the span of this vector. Okay, it should be in the span of this vector. I will show you in an example what I mean exactly. But this is exactly what's going on here. And you'll see why this is needed. So just if you bear with me.
Here, what is g of x? Is the constraint? Or
What's that?
what is the g of x here? Is it the constraint or what?
Yeah, g of x is not the constraint. G of x represents the final set. The target set. Sorry, it's the target set of the final state. X at T1, right? It's a set. Okay.
More general case of what he's talking about. I think on a previous example we did where we had a constraint and we knew with the Lagrange multiplier that the gradient of the constraint was parallel to the gradient of the function.
Yes.
That means they would share the same, they'd be normal to the same tangent.
Right. Yes.
But, okay.
Yes. So let me go back now. Yes, now I'm here. Okay, so that's the definition. That's the definition of the tangent, and that's the definition. That's the definition that we would like to solve for P of T1. Okay, so if you go back to the case to special case 1, right? We did not know the boundary conditions on P. We used the boundary conditions on the system, x at T naught and x at T1. Now x at T1, we are given in the problem that it could be anything, which means that we don't have a boundary, a final boundary condition. So we cannot solve the states and co-states unless we have the boundary conditions. So how to get the boundary condition? This transversality or orthogonality condition will be a satisfactory condition to use to get what is missing, the boundary condition that we are missing. Now, if S1 is the whole space, then as I mentioned, x of T1 can be anything, okay? So that means this tangent is the whole space, and the only P of T1 that can satisfy this condition in that case will be equal to 0. Okay, so in that case, so if I have this case here, then immediately I know that P star of T1 is equal to 0. Okay, so so the minimum condition is the same. We want to find U such that, or U star rather, such that the Hamiltonian at U star is less than or equal to the Hamiltonian at any other U, which makes the Hamiltonian here a global minimum as a function of U, okay? And if the problem is time invariant, if the system does not depend on T, right, then this is true. This must be true. That is, the Hamiltonian at X star, P star, U star is equal to 0 for all time. Okay, so the proof of this is, or the analysis of this is provided in section 515 of Athen and Fab. Okay. So we go back now here for a second. So basically, so now, before I go to the example, we consider two special cases, special case number 1 and special case number 2. Special case number 1, x at T1 is given as xf. So we know exactly what the final state needs to be, okay? And so this is the given, this is the optimal, obviously, that it needs to satisfy that. And in that case, we did not use the P star at T1. It's free, it could be anything, right? And in fact, analysis could show that might, the choice of the boundary conditions of P could affect the time if the time is not optimized. Special case 2, we have two subcases in that case. First one is that x of T1 is free, right? Which means that S1 is the whole R plane, okay? In that case, P of T1 is equal to 0. But if x of T1 belongs to some set, right? Then that's what we need to steer x1 of T1 to, right? And in that case, this needs to be satisfied. P of T1 needs to be perpendicular or orthogonal to the tangent space at x star. Okay, so it has to do with the number of conditions that we need in order to solve the problems. So let's go back now and consider an example. This is, yeah, go ahead.
Can we use the formula that we use in the operational approach? It was like a partial derivative of k, I think.
No, here you can't, because this is a constrained problem. So unfortunately, you cannot use the variation in approach. All right, so here's let's go back and consider the time optimal control problem of the double integrator system. Okay, so in this case here, x1 dot is equal to x2. x2 dot is equal to u, and u is constrained between 1 and -1. The initial states are given, and the final state, look at the final state. The final state, we would like to steer the system from this initial state to this final state. x1, so this is a two-dimensional system. x1 at t1 needs to be equal to 0, whereas x2 at t1 is free. Okay, so we don't care, it could be anything, right? And t1 is free, okay, because we want to minimize it in this. So the cost function is, as we know before, this is the cost function. And okay, so how to solve? So we solved this problem before when x2 of t is equal to something. Right? Here it's free, so we don't care about it. So one would expect that the time it would take to steer the system from this initial state to this final state is less, because it's less number of conditions that we need to satisfy. Okay, so we'll see. All right, so the Hamiltonian is the same as before. So we solved this problem, so I'm skipping details here, right? So the Hamiltonian is this, and U star, we did this before, is equal to minus sine of P2 star of T. Okay, so see lecture, I believe, number 5, how we did that, okay? Now, we need to solve for a boundary condition that is missing, because this is a two-dimensional system, right? It will have two co-states, so we'll end up with 4 differential equations. So we need 4 boundary conditions. Okay, so how many do we have? We have 1, 2, 3. We cannot use this one. We don't know how to use this one, right? So we need a 4th boundary condition. And this is where we need the transversality condition. So let's see how we can use it. This is the key to this lecture here. So first of all, the set here is not the whole space, right? The set, this should have been capital S, but anyway, S1 is equal to 2-dimensional. One of them, the x1, has to be fixed at 0. And the other one, we don't care. So this is the set, S1. From this set, okay, we define a manifold, right? That manifold is G1 of x1, G1 of x is just x1, because it's a constant, okay? So, so it's x1. The gradient of this G1 with respect to x is 1 and 0. Okay? Now, the tangent of this G, x1, right, is going to be, as we defined it before, the dg1 with respect over dx, right, times something should be equal to 0. That's, if you go back, that's our definition of M, right? It's dgi over dx defined at x star of t1 times this, right? Should be equal to 0. So from here, right, dg1, so this is the gradient, this is the partial, so it's the transpose of that, so that would be 1 and 0. So this g1 or dg1 over dx is 1 and 0. Okay, what is the vector that if I do multiply it by 1 and 0, I get 0? That's that vector. 0 and something that I don't care about. I use a star here. Okay, so that is 0 and x. That's what what we define as x minus x star of t1. That's the one. That's that vector there. Okay, or that's that space. Okay, to be precise. Now, the transversality condition says that P star at T1 transpose times that space should be equal to 0. And from there, right, what is the vector? What is the row vector that if I multiply by this column vector, I will get 0? Obviously, that's going to be something and 0. I don't care about that something, whatever that is, times 0. Immediately from there, you can see that the condition that I'm looking for is P2 at T1 is equal to 0. It has to be 0 in order for this condition, for transversality condition to be satisfied, this condition to be satisfied. Okay, and from there, I find the final boundary conditions. X1 star at T1 is equal to 0, and P2 star of T1 has to be equal to 0. That's it. Once I found the boundary condition, now it's just exactly the same as before. Instead of X2 star at T1, now I have P2 star at T1. Okay, and that's it. So if you combine everything, you have, so again, we did this before. So P1 dot is equal to 0, P2 dot is equal to minus P1, X1 dot is equal to X2, X2 dot is equal to U, which is equal to minus sign of P2. That's the closed loop system. We call it the closed loop system. The boundary conditions are H naught, U, V naught, and 0 and 0. Okay, and so now we need to figure out how to implement. So this is the optimal control problem. Okay, solving this problem is the solution actually. Okay, it's just now the issue now is the implementation, right? How are we going to implement it? Using feedback from P2, using feedback from time, or using feedback from X, right? Open loop feedback or closed loop. Okay. Sorry, feedback strategy, X feedback strategy, state feedback strategy. P2 is the one that will determine the switching. But if you see here, switching happens when P2 is equal to 0. But P2 is equal to 0 is defined, happens at the final time. So in this case here, actually, there will be no switching. Okay, at least in this special case here. And let me now show you how. 1 second. Okay, so first of all, so the equations, if you solve these differential equations, you'll get P1 of t is equal to C1 and P2 of t is equal to minus C1t plus C2. Okay, now taking or assuming or considering these constants to be equal to be positive, right? Then you have something like this one. In this case here, when P2 is equal to 0, right? Before that was the switching time. Here it's the final time. And it's going to be C2 over C1. Okay, so it depends on the initial conditions of P1 and P2. Okay, if you take now the equations for the state, you have x1 dot is equal to x2, x2 dot is equal to plus or minus 1. Okay, because x2 dot is equal to u. If you solve these two equations, right, then you'll end up with this equation. X1 is equal to plus or minus half x2 squared plus C3. Okay, and these curves are the same as in the book, right? So as also in the previous case, like so it's like the previous case, right? So you have when you have positive u, you'll end up it's from it's up, and then when you have a negative u, it's down, which is this one here. Okay, so this is the phase portrait x1 and x2. Let's go back to our case, exactly the case. So here, whether you have this one, that one, that depends on C3, by the way, right? That depends on the initial and final conditions of X. That's on C3, okay? Keep that in mind. Okay, so the feedback strategy that we have, we could do it using, it depends on X1. So meaning to the right of the arc and or to the left of the arc. The only thing that is different now is that I only care about X1 at final time, not X2. X2 is free. So if I am here, somewhere here, okay, then I should apply U is equal to -1. That will take it up to here. Okay, this is the case when X1 at T1 is equal to 0. And it doesn't matter where it lands on the y-axis because I don't care. Okay, X2 could be anything on the y-axis. So the only thing that we care about here is to drive X1 from anywhere to 0. Okay, and the trajectories will obey this curve because that curve is exactly that one, the parabola equation. Okay. Similarly, if I am in the left half plane and if X1 is negative somewhere here, right, I apply positive, U is equal to 1 plus 1, right, and that will drive it according to the parabola to somewhere on the y-axis, and that's it. Okay, so we reach to X1 is equal to 0. Now, the time to stop, so you start from any time. The time to stop is C2 over C1, which depend on the initial conditions of P1 and P2. Now, let's verify that, okay? So let's verify this condition. So if you take X1, the initial condition on X1 to be positive, then we apply U is equal to -1. Okay, and assume, taking C1 positive, C2 positive, then if you solve the equation of X1 dot is equal to X2 and X2 dot is equal to -1, right? So the equation X2 dot is equal to -1, if you integrate both sides, that's what you will get. X2 of t minus X2 of 0, right, is equal to the integration of -1, which is from 0 to t, and that would be that, minus t. Take the X2 of 0 to the other side, that's what you will get. Okay, now X1 dot is equal to X2, right? So you take this X2, so you have X1 dot is equal to X2 at 0 minus t, okay? And then integrate both sides, you will get the equation for X1 of t. Okay, so now we have an equation of X2 of t and the equation of X1 of t in terms of t and the initial conditions. Okay, the Hamiltonian is 1 plus P1 star T X2 star plus P2 2 star U star. Okay, now so the equations for P1 and P2, P1 is C1 and P2 is minus C1 T C2. Okay, if you differentiate, if you integrate these two equations, that's what you will get if you solve them. Okay. Notice that we are able to do this in the closed forms because of linearity of the equations. Okay, so substitute by P1, by X2, by this equation, by P2, and by U, in this case, -1, okay, and that. And you will see that the Hamiltonian is equal to 1 plus C1 X2 0 minus C2. So this needs to be equal to 0, and for that to happen, right, X2 of 0 should be equal to C2 minus 1 over C1, which means that there is a unique initial condition for X2 that will satisfy this problem. That's what we want. So everything is well posed. That's what I'm showing you. Similarly, right? So that's the condition of optimality. H needs to be equal to 0 at the optimal point. Okay. The other thing is we want to optimize the problem, but also achieve the final condition. The final condition is x1 of t1 needs to be equal to 0, right? So x1 of t1, so plug in t1 here, and we know what t1 here is. T1 is equal to C2 over C1, okay? So plug in C2 over C1 here, and so you end up with this equation here. Okay, so you have C2 over C1, C2 over C1 squared, right? From this optimality condition, we know exactly what the x2 of 0 needs to be. So if you plug it here, if you plug it in here, you'll end up with a unique x1 of 0. So there is a unique initial condition, x1 of 0 and x2 of 0, right? That will solve the problem when we consider this case here. Okay, so if we are here, right, there is a unique initial condition that will lead to that solution. All right, any question? Yes.
Yes, from the beginning, how did you find the equation of the g of x?
Which equation?
In the beginning of the question, the g of x.
Yeah, this one.
Yeah, this one.
Yes. So in this one here, let's go back to the definition of g of x. So we want, so this is the definition, the set, right? So in this case here, we want to define the set in this form here. G1 of x, G2 of x is equal to 0. In this case, it's easy because x1 is equal to 0. So G, we can choose, so we can choose G1 is equal to x1 because immediately it's equal to 0. You know what I mean? So these are choices. You choose them so to define the final set, the final target set. You know what I mean? So in this case here, it should be straightforward because x1 is equal to 0. So we only have one function, right? And k here could be, so the number of functions here is equal to the number of final states that are given. You know what I mean? So in this case here, the one in the example, x1 is equal to 0 is the only one that is given. So that means I have only one function and it's easy, right? It's x1 is equal to 0. So then g1 of x is equal to x1. All right, any other question? All right, so let me now, 1 second. So I'm going to introduce the next topic, but I'm not going to cover it all. And I'm going to do that next lecture. Okay, so what if? So before we considered what's known as time invariant systems. So what if the system explicitly depends on t? So let me give you an example. Let's say that the system we are considering, so if I go back to the previous one, yeah. Let's say that the system that we are considering is x1 dot is equal to t x2 and x2 dot is equal to u. So there is a t there, right? Or t showing up in the equation explicitly. That makes the problem harder, and that makes the problem time varying problem. Okay, time varying problem. So time dependence is important, right? And so let's say that we have this system where t appears explicitly in the system. We can also consider the case, and by the way, I forgot to mention something. Let me go back to here. Notice here that I told you that when x2 is free, right, the time optimal should be less, right? We can see it from here. Before, we had like a switching. So this time is the switching time, it's not the final time. There is another time that, right? But in this case, that's the final time. So you can see that that could be smaller time, right, than when x2 is given, right? And that makes sense because in that case, if we want to take x2 to 0 also, right? So we need to do something. So we need to go from here, and then we need to go. So this is why, like, it's intuitive to see that the final time is less when x2 is free. Okay, so let's go back here. So how can we solve this problem when the system explicitly depends on t, right? The same cost, same everything, right? And in this case here, the trick is to treat time as a state. So if you treat time as a state, okay, let's call that x of, so we have n-dimensional system, extend the dimension of the system by 1, and call the n+1 state as time. If you differentiate that, x dot n plus 1, that's equal to 1. Now augment everything together, call that xe. So you have the extended state is equal to x and xn plus 1. The derivative of that, the derivative of x dot is f, and the derivative of x dot n plus 1 is 1. And that would be the new fe. We define that as the new fe. Okay, so now the boundary conditions are x naught and t naught. T naught is given. Okay. So that's the initial condition. The final condition, okay, x of t1, which could be free, or could belong to x of t1 could belong to s1, and t1, which is free. So definitely we need the transversality here. Okay, in this case, because in this case it's given in the problem that t1 is free. Okay, so in this case, because we know how to deal with free final state, right, we will be able to deal with this problem, right? So it's so x of t1 belongs to s1, okay, and t1 belongs to r, could be anything. Okay, so in this case here, we define the updated cost. We call it LE, right? In this case, it's going to be a function of xu and x of n plus 1. And if you let u star be the optimal control and x star be the corresponding optimal trajectory, then the optimal trajectory is going to be equal to x star and t. Same thing. The necessary conditions will lead to the co-states, right? Because we need to consider the extended Hamiltonian in this case. LE is equal to PE transpose FE. Now, you know, because FE is equal to F and 1, right? Then you have PN plus 1 just appearing separately. I mean, this is the same as that one. Okay? Because FE, the last one is 1. So multiplied by PN plus 1, you will end up with PN plus 1. Okay? Now, if you look at this one, what is this? This here, right, is So you have L of xu and xn plus 1, right? Which is the same as L of x, u, and t, okay? P transpose F. So basically, and I forgot to stress this, right? That not only we are considering in this case T appearing explicitly in the system dynamics, but it's also appearing explicitly in the cost. So it's appearing here and here explicitly, okay? Or it could be one of them. So if it either appears here or both, that's the same situation, okay? So the same situation. So this is the general case where it appears both here and here, okay? So this is why I have x of n plus 1, which is t, right? Which is that. Now, this part here is nothing but the Hamiltonian, the original Hamiltonian, okay? So the original Hamiltonian plus p n plus 1. So, so I'm going to stop here. I'm not going to finish everything today. But I only want to mention, and I want to invite you to read section 514 in preparation for next lecture, okay? There is only one, it's going to solve the problem. So we're going to solve this problem in the general way as we did it in the transversality, okay? It's, as you can see, it's just, you know, the problem is now set up or formulated in a way that we can use what we just discussed in the previous slides, okay? But there is one problem here that is not going to be, it's not ideal, and that is if stability is one of, there is an issue with this stability. So in general, when you solve this optimal, forget about T for a second, okay? When you solve this optimal control problem, stability of the system is guaranteed. And by stability, we mean, or asymptotic stability, I should say, asymptotic stability means that we need to drive all the states to the equilibrium. And the equilibrium for the system, when the system is linear, it's the zeros, is the origin. But if you define the t as x of n plus 1, right? And when you stabilize the system, because it's free, x of n plus 1 is not going to go to 0, okay? It's going to go to its equilibrium point, which is non-zero. It's a side point. It has some implications on the stability, but it has no implications on the solution of the optimum problem. Okay, so I will stop here and I will take it from here next time. Okay, I'm going to upload the assignment hopefully today, and also I'm working on homework number 3, which will cover up to this topic. Okay. Any question? Yes, go ahead.
One assignment, sorry.
So there is an assignment, 10% assignment for the course, and it's going to be a project, basically. It's a mini project, and this it's basically you're asked to solve a problem of interest using any of the techniques that you learned in this course. And you have until the end of the semester to do it. And it should involve simulation, software simulation, and optional hardware even implementation. So I'm finalizing it, and we'll discuss it next time, okay? All right, thank you guys. See you next week. See you next lecture. Thank you.